Hello, this is Mr. Gilmore with the 1.3 matrix multiplication lesson. Today we're going to learn how to multiply matrices together, and we're actually going to find many uses for the product of matrices. We'll see that this will actually continue on in many following chapters of what it looks like to multiply two matrices, or even more than two matrices together, and what that product looks like. Where we start is actually with a familiar product to us, and that would be the dot product. We can actually form a dot product of n vectors. So let's let A and B be n vectors. Remember, n vectors are those that we form each element within a individual row, and we put that in just one column. So we have A dot B is really then very similar to the way we, actually not really similar, it is exactly the same way we saw it within our multivariate calculus, where we were multiplying, find the dot product of two vectors, and that is we multiply each of the respective elements together and then add those results together. And so what we're doing is the first element of A times the first element of B plus the second element of A times the second element of B. And we add all all the those values up. So we basically have the series of this product, and it then results in what we call a dot product. So an example down below, we have two vectors u and v. They're both the same size n vectors, so they're both 4 vectors, which means if you take a look at how this unfolds, I'm going to do each of the first row elements multiplied to each other, so 1 times 2, and then I'll do my next row elements, -2 times 3, third row elements, 3 times -2, and then fourth row elements, I have 4 times 1. And I add all those results up, and I get a dot product of those vectors to be -6. So that's actually kind of the elementary first approach to multiplying matrices, as we see that those really are two matrices. They're both 4x1s. And you'll notice that just like the dot product did in multi-V, that it actually produces a scalar. So now what we're going to be looking at is bringing two not necessarily n vector matrices together. We're going to look at two matrices that have different now dimensions to them, and how would we multiply those? So we have to then define what does it look like to then do full matrix multiplication without actually having something simple as just an n vector. So here's how this works. Okay, this is really the kind of meat and potatoes of today's lesson. Let's then talk about how do we actually multiply two matrices together. Well, the first thing I want to point out when we want to multiply two matrices together is the dimensions of each matrix. Okay, the first matrix we have defined is matrix A, and its dimension is an m by p matrix, meaning there are m rows and p columns. Let's define a second matrix, B, but notice what its dimension is. The dimension of B is a P by N matrix, means that it has P rows by N columns. What this is actually going to do whenever we multiply these two matrices together, A and B, it will produce a new matrix. We'll call that new matrix C, and that new matrix C, will be an M by N matrix. Notice that it takes the rows from our first matrix A and the columns from our second matrix B, and it forms that size dimension matrix C. That's what it's going to form for C, the M by N matrix C. So in order to actually to do matrix multiplication, you have to watch the dimensions of the matrix. Basically, those inner dimensions, right? If you take a look, if we actually write this out, right, as and you'll see this on the next slide, where I have M by P and then P by N. Those inner dimensions, right? Basically, the columns of my first matrix have to be the same, but they have to be the same amount as the rows of my second matrix. So I have to have those values of P have to be the exact same. If I'm trying to multiply two matrices and those inner dimensions are not the same, then I can't multiply them. That's the first thing I want to point out, is that you can't multiply every single matrix to any other given matrix. You have to make sure that there are the same amount of columns in the first as there are rows in the second. We'll talk about some properties of multiplication here in just a little bit as well, now that we're looking at kind of the definition of our product AB. All right, so then how do we form then the elements of our matrix C? Well, take a look then at each element of C. This, remember, we say C, the lowercase c is the ith jth element. So the lowercase c ith jth element is actually defined then to be equal to this series of looks like products of some element of A and some element of B. And it's a little kind of hard to see, you know, kind of what's going on because you've got all these different letters. You've got I representing rows, you've got J representing columns, you've got these different subscripts of, you've got a subscript of 1, and then a subscript of 2, all the way to a subscript of P, and it's showing that this is really what you're doing. You're taking the element of A, the ith kth element of A, and you're multiplying it to the element of B, the kth jth element of B. And of course, I again is listing out from 1 all the way up to the number of rows m, and j is listing out from 1 all the way up to the number of columns n. But here's kind of what that picture looks like. I'm give a kind of a better picture what that looks like. Is this, in other words, part right down below at the very bottom of the screen. What we're going to do is we're going to take the row, right, the ith row of A, and we're going to transpose it. So if you think about a row, right, a row has n elements in it, 1 through n elements. And remember when we transpose, we saw this in the last lesson, we take the row and we turn it into a column. So we're going to take that row, the ith row of A, and we're going to turn it into a column. And the number of elements in that row, now this column, is going to be the exact same number of elements that we're going to find in the columns of B. And what we're going to do with that is we're going to form the dot product, because when we transpose the row of A, we form it into an n vector, and that n vector will be the exact same, has the exact same elements of each of the columns of B. We think of columns of B as being these individual n vectors. And so now that's kind of a new way of thinking about a matrix, is that we can chop a matrix up into its n vectors, which are these columns of the matrix. And what we're going to do then, again, we take the row of A, right, the row of A, and we transpose it to form a column, which is that n vector, and we dot that with the column of B, and it's going to form the element in C. It's going to be best to kind of visualize this in terms of an example. So the first thing in our next slide here that I want to point out is just go back to watch the dimensions of each matrix, because not all matrices can be multiplied together. You have to watch those dimensions. And I talk about those in the inner dimensions being those p-values. So notice how the p-values here are the same, right? When those p-values are the same, that means we can multiply these matrices together. If they are not the same, then we are not allowed to actually form the product of these two matrices. So if A is a matrix of m by p and B is a matrix of p by n, we can then form the product of AB by m, which is going to form a matrix C of an m by n matrix. All right, so let's take a look at the breakdown of matrix multiplication with these this example here of matrix A and matrix B being multiplied together. So how this is first going to work is I'm going to take my first row, the first row of A, which is this row right here. This row had the elements of 1, 2, -1. And what I'm going to do with that row is I'm going to transpose it. So I turn that row into a column. And that column becomes a column of 1, 2, -1. And then what I'm going to do with that column is I am going to dot that with the first column of B. And what we'll find there is I've done that now down below here. There's my transpose of my first row of A, and there is my first column of B. And I'm going to dot those two together. Remember, a dot product is now simply just like we did MB, is we multiply each of the row elements together and then add those together. So notice that what this was row 1, column 1. Okay, row 1, column 1. And what that does for us here is that is going to form the first row, first column element, meaning it's going to give us that new element of our matrix C, right? We can define this new matrix to be C as 1, 1. Right, so C1, 1, because we have the first row, first column. So the first row, first column element of C is going to be the dot of those two matrices, those two n vectors. So I have 1 times -2 is -2, 2 times 4 is 8, and then -1 times 2 is -2. So I have -2, -2, and 8 make 4. So there's my first element. And now I repeat that process for however many rows and columns there are. Now I've used my first row and multiply to my first column, but there's another column I can multiply by. So I'm going to use my first row again, and I'm going to multiply it now. Instead of by the first column, I'm going to multiply it by the second column. So I'm going to dot that n vector, the transpose of my row, which turns into the n vector, to the column, second column of my my matrix B. So now look at our next element down here. This is still row 1. Okay, I should say the transpose of row 1. There we go. Transpose of row 1. So that 1, 2, negative 1. And I'm going to dot it with now my column 2, right? My second column. And if you take a look at our subscripts, 1, comma, 1, 2, that's going to form now the next element, C sub 1, 2, which is the first row, second column, right? Because I use my first row, second column in my dot, right? The transpose my first row, dot with the second column of my matrix B gives me my next element in my matrix, my first row, second column element. And that gives me negative 2. And you can check my math there, but I'm not going to walk through every single dot there. But there's my my element I get was negative 2. All right, now I've used up row 1, the transpose of row 1, I've actually done that to all my columns. So if I had more columns, I continue that process to then finish off the first row of my product matrix. Okay, so now I go on to my second row, and I take my second row, which has the elements 3, 1, 4, and I transpose that. So it becomes then 3, 1, 4 into a column. And that's my row 1, and I'm going to then dot that with my column 1. Sorry, not row 1, row 2, and I'm going to dot that with my column 1. And so notice that what this one is, this is the transpose of row 2, right? Transpose of row 2. And this guy right here, this column is the first column of my matrix B. And I dot that to form a new element. And notice again my subscripts, I have a 2 there, row 2, column 1. Well, that's the element that's going there. That's my C sub 2, 1, right? The second row, first element. And I repeat that process one more time. I take the transpose of my row 3, 1, 4, and I'm going to dot that with my second column. And what I get there then, as you see, I have my second row, the transpose of my second row, and I dot that with the column C sub 2. And what that means is I'm going to have my element be C sub 2, 2. That's my second row, second column. And that produces, right, you check my math, my dot there, that produces that element 16. And so that is then the product of these two matrices, A times B, right? This matrix multiplication, AB. And man, sorry about that. Notice then, I should have expected that I really would have only ended up with a 2 by 2 matrix, because if I start off with looking at my element, my example A here, A was a 2 by 3 matrix, and I am multiplying that by, right, so this is being multiplied by, how do I want this? Yeah, I'll do it this way. So this is a 2 by 3 matrix multiplied by this 3 by 2 matrix. So I notice that my inner dimensions are the same, check. But they disappear, right? Because what they form is we take our outer dimensions here, 2 and 2, and that's going to form our new size matrix. So that 2 by 3 multiplied to a 3 by 2 is going to turn that into a 2 by 2. Now we'll learn and interpret, what does this mean, right? What is this? What am I really doing if I do matrix multiplication? Right now, all we're just discovering is just multiplying them. Just the process of multiplying them. It's going to be an important step along the way. We will learn later on about interpreting matrix multiplication. Like, what does it mean that I've done a 2 by 3 times a 2 by a 2 by 3 times a 3 by 2? What is that? What does this resulting matrix actually tell us? And we'll learn about what that looks like as we progress down the road. But right now, we're just learning the elementary portion of matrices, and that is, you got to know how to multiply them together. Okay, let's continue our journey talking about matrix multiplication, and we'll learn a couple now more details about the product of a matrix. So let's say let's assume that there is a product, an A by B matrix that exists, meaning that the dimensions of A and the dimensions of B, they satisfy the product, which means that the matrix is produced, right? There is some sort of product matrix produced of AB. Well, then let's talk about BA, right? So I'm actually then reversing the order of our multiplication there. So in the first we did A times B, we say that exists. Let's talk about what happens if I were to do B times A then. Okay, so B times A, there's four possibilities. There's four things that could possibly happen. The first thing is it may not exist. Because if you think about what the dimensions are of what we defined the dimensions of A to B, right? We said A was that was an M by P matrix, and B we defined to be a P by N matrix, which then is fine, right? That means that this exists. There is some AB that exists that's an M by N. But if I reverse the order, right? I reverse the order. If I were to do this, B times A, well, that means it's a P by N matrix times an N by P, an M by P matrix. This may not exist, and actually we have to consider what these dimensions are, this N and M. If they are not equal, well, then we can't multiply those together. And that's why BA may not exist. All right. So there are some interesting, unique properties to the matrix whenever we are multiplying matrices together. So that's the first possibility that could happen with B times A. A second possibility, it means it is defined, right? That means that M and N are equal. And that means there is a defined matrix. In other words, what would happen then is BA would become a P by P matrix, as you see that, if M and N were equal. Then they become a P by P matrix, which is a square matrix, while AB then is an M by M matrix, because remember, M and N we said to be equal, and so if these two are actually the same, then our AB would then become it's also a square matrix, M by N, M by M, or an N by N, either way we put it. And that is also, thus, if M and P are not the same value, then A, B, and BA are different sizes, because you have an M by M and a P by P. We're not guaranteed that M and P are be the same integer value, which if they are, then yes, they will be the same size, which leads us to another conclusion, that A and B, so this is our third conclusion down here, then BA and AB are both the same size, and they may even be equal, meaning that the elements of AB are the exact same elements of BA. Right, they match up exactly. Or the matrices may be unequal, meaning the elements of AB and the elements of BA are not the same. So there's a lot of different conclusions we can arrive to when we were to reverse the order of our multiplication. I hope you guys are beginning to see kind of the evolution then of our matrix properties. Our matrix properties are non-commutative. Right? Just because I do A times B is not going to be the same thing as B times A. We will look at properties of the special matrices of where those are the same, where A times B is the same as B times A. We'll learn something about our matrix B at that point. But as you see, there are many different possibilities for BA, none of them being fully conclusive until we work with specific data. And so we have to be very careful with reversing the order of multiplication, right? Because we have to watch those inner dimensions, making sure we actually can do that. All right, let's take a look at some examples, just kind of following through with what happens if we look at BA. So here's the first one. If A is a 2 by 3 and B is a 3 by 2, that means AB is a 2 by 2 matrix, but BA is a 3 by 3 matrix. We see that the order we multiply through actually changes the dimension. And again, we'll be interpreting what these dimensions do later on. You know, what does it mean if I take a 2 by 3 and a 3 by 2 to produce a 2 by 2 matrix? What does that actually interpret? What does that tell me? We'll get to that later. Another one, if A is equal to the following defined matrix and B is also equal to the following defined matrix, then we see that the AB, which is a 2 by 2 times a 2 by 2, we are going to end up with a 2 by 2. We get the following result for AB, that matrix. But notice how different that is, because we can do B times A. They have the same inner dimension. We also get a 2 by 2, which means they are the same size, same dimension. However, BA, as you see there, has different elements, which means AB is not going to be equal to BA based on the order of multiplication there. So what we're finding there is that the order multiplication is important. We will find later on when we are working with matrix equations that when we multiply each side of a matrix equation, we have to then make a choice, and we have to be very careful. We will either do a pre-multiplication, which means that our multiplication will go in front of the given expressions on the left and right, or it will be a post-multiplication, which means it'll go behind the matrices, either on the left or the right side of our equation. So we'll talk about those. We have to be careful with pre-multiplication and post-multiplication. There is a difference there as we look at our multiplication of matrices. Okay, let's continue on and let's take a look at matrix vector products. So one thing we can do is if we define a matrix to be an m by n matrix, we can actually multiply that now to a vector matrix or an n vector, I should say, because our n vector we define to be an n by 1 matrix, and if we have an m by n matrix to multiply that to, then we will actually produce what's called an m by 1 matrix, meaning we get then a matrix that has the same number of rows as A does, but now it's actually a different size, maybe different size than our n vector matrix is. What we can do with matrix vector products is we can actually form a linear combination out of this product. So notice that we have let A be multiplied here to our n vector C, and because of that, that means since we produce this this m by 1 matrix, we can actually form a linear combination of that m by 1 matrix. And how that works is what we're going to do is we steal the coefficients, or basically the elements, out of our matrix, our n vector C, and we place those and we make those as coefficients of our linear combination. Okay, so each element that was inside of our n vector, so c sub 1, c sub 2, all the way to the very last element in that n vector, c sub n, we're going to let those be the coefficients. And then what we do is we take apart our matrix A. Because matrix A has n number of columns, we can actually then pair those in a linear combination form with each of the elements that we find in the respective row of the n vector. So this, when we read this, this is the first column of A. So basically we are dissecting our matrix A, and we form the first column of A, and we're going to form a product of our first element of C and our column of A, and we do that again with our second element of C with our second column of A, and so on, so on, so on, until we have our very last element of C forming a product with a scalar product with our last column of A. And this all together, if we add that all back together, it actually forms then our multiplication of our original A times C. So it's kind of another way of actually multiplying, thinking about how we can multiply. Instead of actually walking through, taking each row and forming a dot product with the column, we can actually break up each one of these as saying it's really a scalar. It's really a linear combination of a scalar times each column. And then we add all that up. It's going to form that m by 1 matrix. That's what it's going to form for us. All right, so let's then take a look at a kind of example what that looks like. So what I could do if I were to actually multiply our matrix A to our n vector C, notice that is a 2 by 3, and then this is a 3 by 1. So I know I'm going to get a 2 by 1 matrix out of this. I could do my first row times my column here of C, and then my second row, and dot that with my column of C again. Or what I can do is I can use my linear combination form to form what the product of our matrix A and our unit vector C is. Not unit vector, just n vector C is. So here's how we do it. We steal the first element of our n vector C, and we turn that into a coefficient. So we make that a coefficient 2. It basically is going to be a scalar 2. And what we're going to do then is we are going to dissect our first column of A, chop that out, and we are going to then form a scalar product of our first element and our first column. So 2 times the first column of 2, 4, that is going to give us some 2 by 1 matrix that we are then going to keep producing then with our other columns, and then find the sum to then produce what really is the product of AC. So now I'm going to take my second element, -3, and I'm going to pair that with our second column, boop, and then I take my last element, 4, make it a coefficient, my scalar product, paired with our last column there. And as we see, we can then find what our final matrix looks like by then following through with each of these scalar and then sum. So I have 2 times 2 is 4, -3, -1 is +3, so that's going to give us 7, and then 4 times -3 is -12, so then 7 minus 12 is -5. I can do this again. 2 times 4 is 8, -6 is 2, -8 is -6, and there we have it. There's my end product. But we can generalize this. Instead of doing it with just a matrix to a vector, an n vector, we can actually do this same sort of generalized process with two matrices. All right. And how this works is we take the product of our two matrices here, there's our product of our two matrices AB, and we form the individual columns of our product. And we can form those individual columns by thinking of it in two ways. Okay. Really, what this is we would steal so we think of from B. So let me actually highlight B here. So from our value, from our vector, our matrix B, we steal the first component of a column and we turn it into a coefficient. And then we pair that with the first column of A. And then we take the second component of our column in B and we make it a coefficient. And then we pair that with our second column of A. And we repeat that process until we've used all the elements within that column of B as a coefficient, and we used all the columns of A, and we form then this sum, which actually turns out to simply just be the product of A times the column B, because this right here, the column of B, right, the jth column of B, that is really just an n vector. Okay, that's just an n vector. That's what it is. And that's what we're seeing up at the top is just A times some n vector, right? And we can rinse and repeat this for every single column we have. So, of course, we want to start with the first column of B and then move on to the second column of B and then the third column of B, and we can rinse and repeat this. So let's take a little example of actually using this generalized form of breaking a product of two matrices up into basically what we call the linear combination form. Now, with the product of two matrices, we'll take a look at it. We have to, depending on the size of it, we have to look at basically each component in column form, because what's going to produce is only one column of our resultant product. Now up at the top here are our two matrices, A and B. So this is matrix A, this is matrix B, and I've gone ahead and found the product of that just so you can see the end result that does match up. So this is a 3 by 2 times a 2 by 3, which is going to give us our 3 by 3 matrix. Now, by doing this, you see that I could take my first row multiplied then by my first column, and it produces 4. Then I can do my first row times my second column, and it produces 7. And then first row times my third column, and it produces 6. When I say times, I mean the dot, right? Dot it with each of those. So I could do that for each one of the 9 elements and rinse and repeat that, or I can actually find each of the columns one at a time of my product. So here's how I could do it. Let's look at the very first column of AB, right? AB is my product. So how would I do this? Well, what I'm going to do is I'm actually going to look at my very first column of B and treat that first column of B like an n vector. Okay, like an n vector. Meaning I'm going to take my first element, -2, and that's going to become a coefficient. And then I'm going to match that up with my very first column of A. And I can then find a very simple product, right? Multiply -2 to each one of those elements. Then I keep going because I want the entire column, and that entire column then would be, I take my second element in my first column B, which is 3, and I pair that up with my second column of A. And by finding the then result of this scalar product and then the sum of these two n vectors, I produce, take a look at this, 4, 6, 17. That is the first column of my matrix AB. So it helps in some cases to speed up the multiplication of matrices. If you're trying to multiply matrices together, sometimes the products can be really nasty. Well, instead of actually working through the row 1 times column 1, row 2 times column 2, we can form a linear combination of the product for each column. All right, so let me clean this up a little bit. And then let's take a look then at just repeating that process for column 2. So for column 2, I would then look at column 2 of B. And for column 2 of B, I steal out my first element, 3. That becomes a coefficient. And then again, I pair that with my first column of A. There's that 1, 3, -1. And I rinse and repeat that. I take my second of b, which is 2, and I pair that with my second column, 2, 4, 5, and then I just multiply through. Okay, so 3 times 1 is 3, plus 2 times 2 is 4, so 3 plus 4 is 7. 3 times 3 is 9, plus 8, 17. Negative 3 plus 10 is 7. And there we have it, right? So a very fast way of then doing this by hand is break it up into a linear combination form of our two matrices A and B. So I hope that that makes sense as far as looking at the breakdown of using a linear combination and our matrix vector product to actually form the product of two matrices much easier than trying to have to do a row times column every single time. Now, I'm not saying the row times column is a bad thing. I'm just saying there are some cases it may be faster for us to actually find the product by breaking it up into a linear combination form. All right, we just have a few more things to discuss here, and then we'll be ending these videos. Let's talk about linear systems, right? Linear systems. This is something that we started in 1.1. Remember what a linear system looks like. We have an example there. Consider the linear system of m equations and n unknowns. Well, here's what we can do with linear systems. We can express them as matrices now. Here's what we're going to do. In the linear system, each one of the linear equations, for each of the n variables that we find there are the n unknowns within each equation, we're going to steal each of their coefficients, and we're going to form a coefficient matrix, which is what we look down below. We have matrix A defined as the coefficients of our linear system. So we call this the coefficient matrix. Okay, so this is the coefficient matrix, and you'll read that in the text, coefficient matrix. Well, what do we do with those unknowns? Well, we form an n vector out of them because there are n unknowns, so we can form an n vector out of them. And we form this n vector of each one of our unknowns, x sub 1, x sub 2, all the way up to our nth unknown, x sub n. And in our linear system, we had, of course, these b values defined as them being some either expression that results from each of our linear equations, which are elements b sub 1, b sub 2, all the way up to b sub n. And we can form another n vector because there's actually, even though it goes down to, an m vector, an m vector. So this is an n vector, right? And this would be an m vector, which actually is what happens when we multiply a matrix to an n vector, we get an m vector, right? This is actually vector or matrix vector product here going on. Hence, what we can do is we can then re-express this entire linear system into this simple then form of really the product of our coefficients A, matrix A, to the n vector of our unknowns x, and it's going to equal then our m vector of the end result, those b values. And so those are notice those are bolded, which means we refer to those as vectors. So we have an n vector and an m vector being produced, or the m vector being produced from the product of our vector and n vector. So it's quite interesting how we take this entire linear system and we can then redefine it in terms of matrices to be something just as simple as that. So that is actually a linear system right there. That's a linear system in a very simple form of expressing it. We are going to find now the use of matrices solving our linear systems much easier. The very last couple slides that I have here is just following up with this idea of taking a linear system and putting it into terms of a matrix. One last little thing about this before we look at some examples is we can augment a matrix together. Let's look at an augmented matrix. An augmented matrix means we basically graft two matrices together. Now, in order to do this, they have to have the same. They have to have not the same dimension, but they have to have the same number of rows in order to graft together. Okay, we can actually graft if they have the same number of columns as well, but typically in augmented matrix, we're going to be grafting such that they have the same number of rows. So what we can do is we can take our coefficient matrix A and our m vector B, which is the values of our B values, we can graph those together. And how we graph them is we basically put them in the same matrix, and we use a symbol to separate where the graft happened. And that's what this dotted little symbol is. In the classroom, though, if you were to ever see me graph these together, instead of using the dotted line, I'm just going to use basically a solid bar separating them, and it looks something like this. So that is what it looks like if I were to graph A and B together in the classroom. I would put a solid bar. I'm not very good at doing the dotted. If you want to do the dotted way, that's fine. I just do basically a solid bar between them. So this is a grafted matrix. This is an augmented matrix here of the same thing, right? Of my coefficient matrix A and then my M vector, my resultant B values matrix there. Which means because remember we just talked about the matrix product, sorry, matrix vector product, we can re-express that also in terms of a linear combination, which means we steal each of the components of our n vector, making those coefficients, and then we pair it up with the column of A, right, which is our coefficients of each of those, and they match up, right? That's the product of that. And we do that again for the second unknown in our n vector, and we pair that with a second column. We do that all the way until we pair them all, and of course then that's going to be equal to our m vector, the resulting product of that matrix and vector together. And so in some cases, the reason why we write it that way, in some cases it does help us think of solutions for our linear system, right? Because that's, right, we're looking for the solution of x sub 1 and the values of x sub 1, x sub 2, and x sub n, all the way to x sub n, that actually satisfy the equations there. So you see that we're looking for the solutions. It's all nice, tight, packed neatly into one n vector. Okay, the last two slides are just looking at examples of taking a linear system and writing it in terms of the coefficient matrix, the n vector and the m vector. We'll augment them together as well. And then last but not least, we'll look at an example where we do it in reverse. And we also will express it as a linear combination. So let's look at this example here. Write the following linear system as matrices A, which is my coefficient matrix, my n vector x, and then my m vector b. Basically, remember how we find the matrix A, our coefficients, is we steal them all and put them into a matrix. This is going to be a 3 by 3 matrix. I have three equations, three variables. So I have my first row would be -2, 0, because there is no value of y there, and then 1. All right, and then I just rinse and repeat that. So 2, 3, -4, 3, 2, and 2. And that produces my coefficient matrix. My then unknown matrix would look like this. Or my n vector of my unknowns would look like this. It would be x, y, and then z. That would be my unknown matrix. And then B would then have my 5, 7, and 3. Oops. I don't know why I did that. Get rid of that line there. 5, 7, and 3. And there's my m by 1 matrix, my m vector. Then last but not least, I can actually augment A and B together. So when we do that, I like to put a little bar in between them. So when I augment them, it looks like this. It's going to look like this. It's my coefficient matrix, and then grafted on, I will have my b value. And again, I do the solid bar there. All right, my b vector. So there it is. That's what it would look like if I were to take a linear system and re-express it in terms of our defined matrices. All right. Last example is to do it in reverse. Let's say I give you my coefficient matrix and my unknown matrix, and then my value of my b values. I can actually then reform this back into a linear system, and I can also write this as a linear combination of each of those. So let's rewrite this first back as a linear system. It looks something simple like this. It'd be 3x sub 1 plus x sub 2 plus 2x sub 3 equals 4. So notice that I just did my first row, my three unknowns, and then my first element of my m vector, and then just rinse and repeat that. So 4x sub 1 minus 5x sub 2 plus 6x sub 3 is equal to 1. There's 0 there for that one, so I'm just going to leave that one out, which means all I have is then a 7x sub 2 minus 3x sub 3 equals 0. And then I have a x sub 1 plus 2x sub 2. I don't have a third. There's just 0 there, so that one disappears, and then that's equal to 2. So there's my linear system, right? And taken back out of the matrix. And then to write this as a linear combination, remember what we do is we steal each of our elements of our n vector and make them coefficients with our columns, right? So there are three variables, there are three columns, and that's what it would look like as I form a linear combination of my three variables, my three unknowns here. So x sub 1 forms a product with my first column, and then I have x sub 2 forms a product with my second column, and then x sub 3 forms a product with my third column. And that's all going to be equal to our M matrix there, B. And there we have it. There's a linear combination. And again, what this can help us do is help us kind of visualize or think better about what our solutions will be for our three values, x sub 1, x sub 2, and x sub 3. Okay? All right, so that is it with our introduction to matrix multiplication. Please be sure you practice matrix multiplication. You've seen it now two ways. We can do it in terms of just the straight up transpose row dot with the column, or you can actually form the linear combination of the matrix vector product to still find the product of our two matrices A, B. Be sure to look at the problem set on Canvas and be working through the 1.3. This is thankfully the last time I have to do this sort of thing with videos. I will be back on Monday to see you guys, and I'm looking forward to that. If you have any questions, of course, please don't hesitate to email me, and I will get back to you as soon as possible. With that, be good and do good. Oh, good golly, Miss Molly. What is going on?